Welcome to lesson 3.2, titled Product and Quotient Rule. In this lesson, we're going to learn a couple more ways to deal with evaluating derivatives for certain types of functions, just giving us some more tools to make our calculations a bit easier. So to start with, let's look at the example that's listed right here to find the derivative. And the function we're given is f of x equals x plus 4 times 2x minus 5. Now, if you were going to try this one on your own, what you might think is a little bit like our properties of limits. I'm just going to go ahead and try to evaluate these two derivatives separately and multiply them together. And what we get would be f prime of x equals the derivative of x plus 4, which is 1, times the derivative of 2x minus 5, which is 2. And f prime of x would just equal 2. There's a couple of problems with that. The first of which, I would be implying that f of x has a constant slope of 2. But if I were to go to my calculator and graph this particular function, we would see that this does not have a constant slope. And in fact, if you can even think about multiplying it out, this would be a quadratic, it'd be a parabola. So the derivative that we have tried makes no sense. But let's think about multiplying this function out. If I were to just rewrite this as f of x equals 2x squared, I would have an 8x minus a 5x, so a plus 3x, minus 20, and take the derivative of that function, we would actually get the true derivative, 4x plus 3. So all this goes to show is that derivatives don't work like limits. I can't just take the derivative of each factor in this product in order to get my final answer. Instead, we have a couple routes. One, multiplying out this function and then taking its derivative, or if that becomes too difficult or we're not actually able to do it, we can follow what's known as the product rule. And what the product rule states is that the derivative with respect to x of two functions, u times v, where u is some function of x, v is a second function of x, this product rule states that we get the derivative by doing the first function times the derivative of the second plus the second function times the derivative of the first. And that's the way I would like you to think about saying this to yourself. And so what I just said, given these two functions, we can take the first times the derivative of the second plus the second times the derivative of the first. And so really all it will come down to is you being able to recognize that you're dealing with the product of two functions. And what we can do now is go back and apply this to our original example. So let's go apply the product rule to our f of x function over here. Product rule would state that f prime of x is the first, so x plus 4, times the derivative of the second, which would be 2, plus the second, the 2x minus 5 function, times the derivative of the first function, which would be a 1. That was our u function. That was our v function. Multiplying this back out, we would get 2x plus 8 plus 2x minus 5, which gets us to the same derivative that we knew to be the correct answer, this 4x plus 3. So let's try a couple examples where we don't already have the answer beforehand. Find the derivative of the following. F of x equals 3x squared plus 2x minus 3 times the quantity x minus 1. I see one function, which we can label u, times a second function v. And product rule states that f prime of x will equal the first, left alone, times the derivative of the second, which is 1, plus the second left alone times derivative of the first, and the derivative of that u function will be 6x plus 2. And if you choose to multiply and simplify this expression, this is the final derivative that you would get, 9x squared minus 2x minus 5. I'm going to leave that part as optional for now because I just want you to get used to using the rule. Moving on, let's try the function on the right. Y equals quantity 2x to the negative third plus 4x plus pi times the quantity 4x plus 1. So we'll go with our dy dx notation. And notice my u function, v function, two separate functions of x being multiplied. We're going to take the first function left alone times the derivative of the second, which is just 4, plus the second function left alone times the derivative of the first function, which would be minus 6x to the negative 4 plus 4. And don't forget, pi is a constant, so the derivative of that constant will be 0. And again, skipping forward to the final simplified answer, the final answer in standard form would be 32x plus 4 pi plus 4 minus 16x to the negative third minus 6x to the negative fourth. On both of those, if you wish to do the algebra in the middle, please go ahead and try it on your own. That's why I left a little blank space here, and I would recommend you do the same. Moving ahead, let's look at an evaluation problem. where we have f of x equals square root of x times the quantity 3x squared minus 3, and we want to find f prime of 4. And the reason I want to bring up this example is to make a point. And that point is, don't use the product rule if you don't have to. The product rule has multiple parts to it, makes things look a little bit more complicated at first, and there's a higher likelihood that you make mistakes with it. So like when I see a function as shown here, what I'm seeing is, well, that's square root of x is x to the 1/2, still times 3x squared minus 3, but I don't see this initially as a product rule problem because it's an easy problem to distribute. This will give me 3x to the 2 plus 1/2, or 5/2, minus 3x to the 1/2. And now it's just a power rule problem, and I don't have to worry about the product at all. If you apply product rule, you'll still get the same answer I'm about to get, but you're going to have to go through more steps. Using this simplified form, though, we can quickly get f prime of x equals 5/2 times 3, or 15/2, x to the 3/2, minus 3/2 x to the negative 1/2. And we're ready to evaluate this at an x value of 4, which I'm going to go ahead and plug into a calculator in order to confirm our answer. And so you can see I already have the function written up. I'm going to use the original function just to make sure we're 100% positive on the final answer and get 59.250. And just to confirm to you that this matches what we see right here, I've also typed in that expression, and this actually says 59.25. But remember, that's one of the limitations of the calculator is that differentiation tool doesn't always get us 100% accurate. Moving on, the second part of our lesson concerns what's known as the quotient rule for dealing with anything that is of the form one function divided by another. So if I look, something like f of x equals x minus 5 over 2x plus 1. Again, you might think like at the beginning I could try just differentiating the numerator and denominator, just like what we would have seen with limits. Well, you can probably guess that this will not be the case, because again, this would imply slope is always a constant value, always 1/2. But if I graph this function, you'll see that that slope is definitely not a constant 1/2. So this cannot be our derivative. Instead, we follow what's known as the quotient rule. The derivative with respect to x of a function u, where u is a function of x, divided by v, which is also another function of x. The quotient rule states that that derivative will be v times the derivative of u minus u times the derivative of v all over v squared. So notice, this one looks similar to the product rule. We still have v du and u dv, except we are subtracting and we end up dividing by the lower function squared. The trick that I use to remember this is to call the top function in the numerator the high function, the function in the denominator the low function, and the quotient rule is as follows. Low, d for derivative of the high function, minus high d low, all over low squared, the bottom function squared. Again, you find your own way to memorize this, but make sure that we are getting this quotient rule locked into memory so that we can utilize it. And applying it to the example that we have at the bottom, here's what our derivative will look like. F prime of x will equal, and again, I've got v and u, or low and high, however you want to do it. So it'll be the bottom function, left alone, times derivative of the top, minus the top function, left alone, times the derivative of the bottom function, all over the bottom function squared. And once again, I've drawn in and left some space to show you that this is what our f prime function will eventually simplify to, 11 over the quantity 2x plus 1 squared. So you can take a moment to do that algebra on your own and see if you can get the same answer. Simplifying is something that I would like you to push yourself to be able to do. Moving on, let's try applying our quotient rule to these two functions listed here. But again, I want you to make the same note we made with the product rule. Don't use the quotient rule unless you have to, because just because something is written as a quotient does not mean quotient rule needs to be applied. If I look at this first function, f of x equals 3x plus 1 all over 2x squared, remember from our power rule lesson that I could take 3x divided by 2x squared and get 3/2 x to the negative 1. And 1 divided by 2x squared will be 1/2 x to the negative 2. And that's just going to make for a much easier derivative, because now f prime of x equals negative 3/2 x to the negative 2 minus x to the negative 3. And again, starting to get ourselves looking to simplifying our expressions, f prime of x would end up being negative 3x minus 2 all over 2x cubed. For the example on the right, though, notice I'm not dividing everything by one term, I'm dividing it by 2. Algebraically, I'm not going to be able to split this one up into 2 terms like I did over here in my example on the left. So this one we will have to apply the quotient rule. And so we'll go dy dx equals, again I've got u and v, so we're going to take the bottom function, 3x plus 1, times the derivative of the top, which is 4x, minus our top function, times the derivative of the bottom function, all over the bottom function squared. And simplifying, we will get dy dx equals 6x squared plus 4x all over the quantity 3x plus 1 squared. And what we'll finish up with are some special problem types. The first one involving horizontal tangents, making sure that we are at all times recognizing the connection between derivative and tangent lines. And so this problem wants us to find all horizontal tangents for this equation, y equals 2x squared over 3x plus 1. But all we really need to think about is what a horizontal tangent is going to mean to us. If I have any sort of curve, a horizontal tangent would be any spot where our slope equals 0, or where our derivative equals 0. So that's all this problem wants us to do, is find all spots where the derivative function is equal to 0. Now scrolling up a bit, what you may notice is this is a function that we've already used. We already know its derivative. dy dx equals 6x squared plus 4x all over the quantity 3x plus 1 squared. All we need to think about is, when does it equal 0? The thing to keep in mind on this one is that it is a rational function. So to get a fraction equal to 0, I would need to have 0 divided by some non-zero number. Recall that if I have a number divided by 0, that is the spot where a fraction is undefined. So I want to specifically set up my derivative so that only the numerator is equal to 0. So that's 6x squared plus 4x is equal to 0. For this particular function, I can factor it. I can factor out 2x from both terms and get 3x plus 2. And setting each of those equal to 0, this first factor will give me x equal to 0, and the second factor will give me a value of negative 2/3. And these are both spots where y has a horizontal tangent. The only thing to keep in mind is check back with the derivative. Neither causes you to divide by 0, so they're both okay. If either of them caused you to divide by 0, we would have an indeterminate form, and that would be a different issue. And finishing up, we have 5 examples at the bottom where we're trying to find f prime of 4, given some information about this function g, this function h, and their derivatives, all evaluated at 4. And this section is just a way to test your application of the derivative rules we've learned so far. What I would suggest is pause before you complete this section and see if you can figure out these problems on your own. If you can't, if you think the notation looks a little bit too weird, maybe check out the first 1 or 2 that I'm going to write up and then try them on your own. And if you try to attack the problems the same way we've done all the others, you'll get through them relatively quickly. So go ahead and pause now. So I'm going to go ahead and try example 1. F of x equals g of x minus h of x is how I'm defining this function. And I want to find f prime of 4. Well, the first thing I need is f prime of x. Differentiating the right side, well, derivative of g of x is g prime of x. This is a difference, so I know I can differentiate these separately, and I'll get g prime minus h prime. And evaluating that at 4, well, g prime of 4, we already know is equal to negative 2, minus h prime of 4, which we know is equal to 5, and f prime of 4, this new function that we made up using the others, will be equal to negative 7. In example 2, we've defined f of x as being the h of x function plus 2. Again, I want to find f prime of 4, so I'm going to start with f prime of x. Still a sum, so I can differentiate these two pieces separately. Derivative of h of x is h prime of x, and derivative of 2 is 0. So finding f prime of 4 will just be h prime of 4, which is going to be equal to 5. For example 3, f of x is defined as g of x plus 2 times h of x. So f prime of x will be, it's a sum, so I can take these separately. Derivative of g of x is g prime of x. And there's my constant multiplier 2, so derivative of 2h of x will be 2h prime of x. And f prime of 4, we'll substitute in the values we know. Now g prime of 4 is negative 2, plus 2 times whatever my h prime of 4 is, which was 5, and f prime of 4 will be equal to 8. Last two, and these are going to both apply the rules that you learned about in this lesson. F of x is defined as h of x divided by g of x, one function of x divided by another. There's no way I can simplify this, so I'm going to have to use quotient rule to define f prime of x, which will be my low function times derivative of the high function minus the high function times derivative of the low function all over that low function squared. And now we can substitute in all of our function values that we need at 4. G of 4 is equal to 3, h prime of 4 is equal to 5, h of 4 is negative 1, g prime of 4 is negative 2, all over g of 4, which was 3, squared. And f prime of 4 is equal to 13 over 9. And finally, in this last example, we'll define f of x as g of x times h of x. So again, I can't simplify this. I'm going to have to use the product rule. So f prime of x will be g of x times h prime of x, first times the derivative of the second, plus the second h of x times the derivative of the first, g prime. So f prime of 4 will be g of 4, which is 3, times h prime of 4, which is 5, plus h of 4, which is negative 1, times g prime of 4, which is negative 2, and f prime of 4 is going to be equal to 17. And that ends our lesson on the product and quotient rule. And at this point, you have most of the tools that we need to differentiate a wide variety of functions. There's one big rule remaining that will come up later on in this unit. The next section, however, will take us into some good application involving some physics concepts. So please make sure that you review and summarize these notes and move on when you're ready. Thank you for watching.